Elon Musk says Starship's heat shield problem is solved. Several former NASA specialists say the current design could be a dead end for rapid reuse. Both sides are looking at the same flight and drawing very different conclusions. So, what did Starship Flight 13 actually prove? What remains unproven? And why could this one technical argument determine whether SpaceX's most important rocket becomes an economic revolution or an extraordinarily expensive experiment? Flight 13 launched from Starbase on July 24th. The 408-foot Starship version 3 completed its suborbital mission, deployed 20 next-generation Starlink test satellites, survived reentry, and made the gentlest ship splashdown SpaceX has achieved so far. The upper stage remained intact and floated in the Indian Ocean long enough for recovery teams to obtain close-up images of critical heat shield and engine areas. 6 of the Starlink test satellites also carried cameras aimed back at Starship. They transmitted unusually detailed views of the vehicle in space, giving engineers another way to inspect the shield before and during re-entry. On SpaceX's August earnings call, Musk said the flight data and visual evidence suggested the heat shield problem was solved. That confidence is one reason SpaceX has discussed attempting to catch the ship upper stage with the launch tower on Flight 14, subject to final data review and regulatory approval. That is the strongest version of the bull case. Starship did not merely survive. It survived in a condition that SpaceX believes is good enough to move directly toward a tower catch. Every test vehicle also carries experimental tile layouts, attachment methods, and materials. SpaceX can compare the damage pattern across thousands of tiles, change the weak areas, and fly again. This is the same iterative culture that turned Falcon 9 booster landings from spectacular failures into routine operations. But here is the distinction at the center of the controversy. Surviving one re-entry is not the same thing as being rapidly reusable. Starship's black ceramic tiles protect its stainless steel structure from extreme heating. Each tile must stay attached despite vibration, pressure changes, aerodynamic shear, and thermal expansion. A missing tile does not automatically destroy the vehicle, but the underlying structure has limits. If hundreds or thousands of tiles require individual inspection after every flight, turnaround time rises. If damaged attachment points are difficult to detect, risk rises. And if large sections require replacement, the economics begin to resemble refurbishment instead of airline-style reuse. That is why several former NASA thermal protection experts have criticized the current architecture. Their argument is not that the tiles cannot survive re-entry. Flight 13 clearly shows that they can. Their argument is that a fragile, inspection-intensive tile system may never support the flight rate SpaceX describes. The Space Shuttle also survived re-entry repeatedly, but its thermal protection system demanded extensive inspection and repair. A reusable vehicle can work technically while still falling short economically. This matters because Starship's promised cost advantage depends on cadence. SpaceX needs frequent launches to deploy larger Starlink satellites, support orbital refueling, deliver lunar hardware, and eventually lift massive AI infrastructure. A moon mission may require multiple tanker launches in rapid succession. If each ship spends weeks being inspected, the fleet must become much larger. That means more vehicles, more pads, more labor, and more capital tied up between flights. The bearish conclusion, however, can also go too far. Flight 13 did not use a frozen production design. Starship remains a development vehicle. SpaceX can modify tile shape, attachment points, gap fillers, local reinforcement, re-entry profiles, and automated inspection. A tile system that needs heavy work today may require far less work after another 10 flights. Falcon 9's current reliability was not visible from its first landing attempts. So the real question is measurable. What happens after Flight 14? Watch how many tiles are missing or damaged. Watch whether the ship is caught or diverted to the ocean. Watch how long SpaceX needs before the same vehicle, or a closely related one, is declared ready again. And most importantly, watch whether SpaceX begins reflying upper stages rather than merely recovering them. A successful tower catch would be historic, but it would still be only the beginning. The decisive milestone is a ship that lands, receives limited inspection, refuels, and flies again on a commercially meaningful schedule. Until then, solved remains SpaceX's engineering judgment, while dead end remains an expert warning, not a demonstrated verdict. For investors, the heat shield is not a side story. It sits underneath Starlink expansion, orbital compute, lunar contracts, and the long-term promise of radically cheaper access to space. Flight 13 moved the evidence in SpaceX's favor. Flight 14 may move it much further. But rapid reuse will be proven by repeated turnaround, not by a single beautiful